Welcome to week 3. This week we're going to focus on systems of stocks and flows. It's a very general approach and it can be applied to many different circumstances. So what I'm going to do is present sort of the basic ideas in this PowerPoint, and then we're going to look at many different examples. And that'll carry through, look at some examples in the text and in the reading and in the application material. The objectives for this short lecture are to introduce the idea of stock and flow systems and give them a few examples, but mainly to focus on how we're going to use these simple models of stock and flow systems to look for similarities across all of these examples. So I'm going to start by defining the stock and flow systems approach, and then I'm going to explain the sort of cartoons or the iconography that we use. And I'm going to use that to explain a few examples. And then I'm going to work through 4 very important concepts. These are parts of models or sort of motifs that you might see in the diagrams. And if you learn to recognize them, it'll really help your ability to apply stock and flow systems to approach problems. So, the idea of a systems approach is to examine the reservoirs and how they're connected with flows of either energy or material. Really, we need to focus on things we can measure or count. So the flow of water or the flow of energy through a system or the number of individual organisms moving around on the landscape. Those are really good examples of things we can model pretty cleanly with a systems approach. And what we're going to do is create a description for the flow of energy and material in these reservoirs, and then try to account for most of all of the flow. And that's really part of the art here. What can you leave out and what can you leave in? And then look at that and sort of predict what's going to happen. That's the purpose of this whole week, would be to try to use these models to predict what's happened. So, for example, if you had the archetypal model that we showed at the beginning here of water flowing into a tub, and you have the water coming in faster than it's draining, a good prediction is that it's going to fill up the tub and go out onto the floor. And that's the type of prediction that at the time it's not flowing out on the floor, but if the same situation continues on, it's going to happen. So that's what we're aiming for in this whole week. But again, in this lecture, we're just going to try to lay the groundwork. So here's some examples of things we might study, and I'm going to be mentioning a lot of examples through the week. Water into a lake, CO2 into the atmosphere. This is a really important one for us now, like how much CO2 is being added to the atmosphere from human impact, how much from natural, how much is being taken up by natural and by the oceans and by plants. And is that balancing it or not? We have energy and material in the nutrition and waste products of individual organisms, such as animals that we might study in ecology or our own human nutrition. And we're going to see some examples in the application reading of energy and material flow through ecological communities or through nutrients or through elemental cycles. So it'll be looking at those things. They're a little bit more complicated, but they still rely on the same sort of stock and flow systems approach. Let's start with a water budget in a lake. This is Upper Klamath Lake, where I do some research, and the picture shows some color, false color of chlorophyll in the lake, showing blooms in particular places. But if we were to do a water budget in this lake, we'd just really want to know how much water is coming in every year, how much water is in the lake at the end of the year, and how much water went out of the lake each year. And then we just add those up and find out, we do a water budget. And that would be just like a budget you might do for your checkbook or your account. These water budgets are very important for things like agriculture and wildlife. In Upper Klamath Lake, for example, a lot of agriculture depends on water that's stored in the lake and used for irrigation. But at the same time, the wildlife, the fish and the birds, rely on a healthy lake that isn't just drained down to mud in order to complete their life cycles and to thrive. So it's very important that we get these budgets right, because a little difference over a long period of time can add up to major problems. Now, in a lake like this, we're looking at the inputs. The gains to the lake would be rivers, springs, groundwater seeping through the ground, rain, and then direct runoff. Direct runoff is what just hits the ground, probably sort of near the lake, and just runs across the ground into the lake. So it might come off ranches or it might come off roads, those sorts of things. And the outflows, in this case, again, the rivers that flow out of the lake. The evaporation is a big loss in this lake because it's in a very warm, sunny place, and over the summer loses quite a bit of water. There's pumped irrigation to support irrigation and agriculture, and there's seepage through groundwater. So some of these things are really pretty easy to account for, like how much is going out of the river. The other thing, seepage through groundwater, that can be quite a problem to measure that very accurately. And again, we're interested in the relative rates. If the input's greater than the output, the lake level rises. This happens in the fall. If the output's greater than the input, the lake level drops. This happens in the summer. Combination of high loss of evaporation and irrigation, the lake is dropping about 1 centimeter per day sometimes. And then if the input equals the output, the lake level stays the same. And this might be just for a short period of time, or I might say over year to year, the lake level pretty much stays the same because they balance the amount of water that was used, and the lake always comes back to the same level by spring. So in order to push this approach to a little bit to be useful in many different systems instead of have just a narrative each time, we use these iconographs, or sort of cartoon images. We have a stalk, which is like a little box, and that represents an amount of something, not moving any place. And then we have sources and sinks, and these are some unknown amount of something, or a destination for something we're not counting. So just like rain might come out of a cloud and hit the ground, and we don't really know how much water's in the rain. That's a source. And then the rain comes down, runs down the street, and goes down the drain, goes into a sink. We can't really count that, but we might be interested in just how much water is hitting the sidewalk, flowing down the street. Then that might be what we would focus on for a flow. But anything that's just outside of what we can measure would be a stalk and a flow. And then we're going to connect the stalks with these flows, and the flows have the characteristic of moving material or energy, and they have some control over the rate. That's the little valve in the icon. And then in order to control flows, we have information flows that control that behavior, and it's just a thin red line. No material or energy moves, just information that might turn on or off a valve, and that's how we can make the regulate a system. And finally, in a model, it's often useful to have just a little comment, or in this case, we call it a converter or a constant. We just might put that in to show that, well, this other factor is affecting the flow, and it's a constant. We would just put it right there. Okay, now when we start to make a systems model, we're going to have 4 key features to look at. First, we're going to set the system boundaries. That's what's inside and what's outside of the system. Everything inside is going to be a stalk or stalk and flows. Everything outside, you could have flows, but they'd be like source and sinks. And then everything in the system, all the stalks and flows are going to be connected, and they have to have the same stuff. You can't mix. You can't mix number of fish with pounds of algae or something. It all has to be the same unit that's flowing in any particular thing. And this constraint is going to help simplify the models, but it's a big challenge at the beginning. And then the next thing we're going to do when we look at this is try to establish a mass or energy balance, just to make sure everything that's coming in adds up to everything that's going out. And that's a good check before you go on any further. And then finally, try to determine what the rates of the flows are and what information is controlling those. So this is just sort of the simple 4 steps if you were going to try to start describing a system with these cartoon iconography. So the system boundaries. Here's an example of system boundary. What's the food that a deer eats and what happens to it? Well, there's a lot of food out in the environment, so that's a source, comes into the deer's mouth. Okay, now we're keeping track of how much it eats, and it's excreted by the deer. Now we're keeping track of how much it's excreted, but it goes out into the dirt. Everything, we can't keep track of that. So there's an example. If you're just studying a deer, it'd be actually pretty easy to just draw a box around the deer and say whatever comes in its mouth or whatever goes out in urine or feces, that's what you're going to keep track of. So here's an example of why that gets a little complicated. The deer here is eating high potential energy organic matter, that grass and other forage. It goes in. Some of that goes out to be burned in cellular respiration to make water and CO2. Some of it is assimilated into the body as new deer. It could be a baby deer. It could be lactation. It could be the deer putting on weight. And the other, it goes out as undigested. There's actual food value to deer poop. And then part of it goes through just undigested. So you've got these combinations. And so this really complicates it. It's not like you have, here's some, grass that the deer's eating and how much grass, because it changes format all the way. So we can try to keep track of carbon or energy, but here's a hint, and if you're facing this, just try to say like what proportion of the food was eaten and what happened to it. So there's 100% of the food came in. What happened? What was the fate in terms of proportion? So, 70% might have been in cellular respiration, 20% might have been as excretion and undigested material, and 5% might have been as new deer biomass. And you try to come up with make your mass balance that way. So one of the things I want to caution you, though, is in our casual conversation, we mix the ideas of mass and energy budgets all the time when we talk about human nutrition. So, for example, we talk about that you ate 2,000 kilocalories per day, and then you had a certain amount of exercise and your normal metabolic rate. And if the intake of energy is greater than your output, then you accumulate energy. But it's not like you're bouncing around like a little super ball. You have actually taken that energy and stored it as carbohydrates or fats. So if over a period of time, like a month or something, you ate 9,000 extra kilocalories of food over what you expended in energy, you would have stored about 1 kilogram of fat. And vice versa, if you expended 9,000 more kilocalories of energy than you took in, you would lose a kilogram of fat storage. But I'm just warning you that we do this so casually and talking about our own human diet, because that energy is really, what you're talking about, it's really as some high energy biological compound that's being stored in your body for subsequent use. Okay, now the control of rates is the next thing to look at. The control of rates is what information flows to control the flow. So here's an example that we're going to see quite a few times during this week, which is the population size is a combination of the births minus the deaths. And the births are actual new births coming in, not the birth rate. The birth rate is something like new births per 1,000 people. So if you had a population size of 10,000, the birth rate would be 10,000 people times that rate. And similarly with the death rate. So what this model shows is that these birth rate and the death rate are constants that feed into the population, but as the population size increases or decreases, the total number of births or the total number of deaths would change. This is the basic underlying model for the population growth and decline that we're going to see. Okay, now there's more examples in the text. And again, just to remind you, start by defining the extent of the boundary of the system, identify the major reservoirs, and then identify the major flows and the factors that control them. Okay, those were ideas about setting up the structure of the model, the sort of cartoon diagram. Now we're going to look for particular control and dynamic behaviors. And there's 4 behaviors I want to talk about. The first is stock limitation, stuff just runs out. The second is steady state, where the stock is at the same level. We saw that in the examples in the lake, talked about that. The third is positive feedback, and the fourth is negative feedback. And these, I want to show you what the model description little part looks like, and then how it behaves. So for stock limitation, you can have a reservoir, an outflow, and then a constant or some other control of the rate. It doesn't have to be constant, but just that the outflow just continuing to go out. And at some point, it's going to run out. The reservoir is just going to run out. There's nothing here to keep it from all being depleted, and unless it's replenished. And so this is a key concept in the difference between non-renewable and renewable resources. Something like nickel in the Earth's crust, that's a non-renewable. It's going to run out unless we find some new sources. Something like trees, you use up the trees, you grow more trees. It's renewable. You'd have something else coming into the reservoir of trees or wood products that would be replacing it. Positive feedback is when the flow rate increases as the stock increases, and I've indicated this directionality of that by the little positive sign over there. Positive or negative feedback are going to look the same. The structural model looks the same. It's just how it behaves. And here's an example. If you have a population of rabbits and there's plenty of food around, and you have a constant birth rate of rabbits in bunnies per month per doe, then as the population gets bigger, there's actually going to be more bunnies born every month. And then the population gets bigger and bigger, then there's more and more. This is that exponential increase that comes from this positive feedback. Negative feedback just has the other sign on the directionality, which just means as the stock increases, the flow rate decreases. It resists the flow is going to resist increasing the stock. And again, taking it from a population model type description, if you have a population that's increasing and increasing as it gets more crowded and as it runs out of available resources, the new births are often decreased, and that's a type of negative feedback. As the population gets very high, the birth rate starts slowing down. That's negative feedback. So I want you to remember that negative feedback is not bad, and positive feedback is not good. In fact, runaway positive feedback is probably the worst thing that can happen. We're maybe facing that with increased CO2 in the atmosphere, which leads to warming, which leads to melting of glaciers, which could lead to more CO2 into the atmosphere through multiple different processes. But that's a runaway feedback that ends up increasing CO2 and heat, and it just feeds on itself. What I want you to look for are well-controlled systems that have combinations. Positive feedback to get them going or get them restarted, like growth of bunnies, and a negative feedback to regulate them at a healthy or resilient population size. So you see this quite a bit in well-regulated populations. The ability to grow rapidly, but also the ability to control the population size at a reasonable value for a healthy community. Okay, now the challenge for this week is you're going to see a lot of examples in the text and the other material in the reading and in the simulation and in the videos. They're going to talk about these sort of positive and negative feedback. And I want you to try to abstract them back just to think about just a stock and a flow and a control and source and sink. What would that look like? And then try to recognize the common features of that in the control system. So in particular, look for positive and negative feedback so that you could recognize